Welcome to Module 2, NumPy Fundamentals. This module covers the foundation of machine learning, focusing on the core library that powers all modern AI systems. This course is brought to you by the Series of Thoughts Tech team. Every major machine learning library, including TensorFlow, PyTorch, and scikit-learn, is built on NumPy. Mastering these fundamentals helps you understand what is happening under the hood of every AI model. NumPy matters for three reasons. Lightning-fast performance, as arrays are up to 50x faster than Python lists. Vectorization power, enabling operations on entire arrays without explicit loops. And memory efficiency, critical for large datasets. This demonstration compares a Python list approach, which requires explicit loops and takes around 100 microseconds, to NumPy array magic, which uses a single vectorized operation and takes only 2 microseconds. Vectorization is NumPy's secret to speed. It processes multiple elements in parallel, using single instruction, multiple data instructions. This is essential for training models on millions of data points quickly. ML algorithms rely heavily on array operations. Neural networks use matrix multiplication for forward propagation. Clustering algorithms compute distances between data point arrays. Decision trees evaluate array conditions using Boolean indexing. To start, you need to create arrays. The most basic way is creating an array from a Python list using np.array. Remember, always import NumPy as np. It is the universal convention. Other creation methods include np0s and np1s for initialization. nprandom.rand generates random values for weight initialization. And nparrange or nplinspace create evenly spaced values. Here we visualize some array creation methods. Zeros gives you a clean slate. Random generates uniformly distributed numbers. Linspace creates evenly spaced values over a specified interval. Understanding array shape is crucial. 1D arrays or vectors have a shape like 5. 2D arrays or matrices have a shape like 3, 4, representing rows and columns. 3D arrays or tensors are common in image processing. In practice, a 1D feature vector has shape 4. A 2D dataset with 100 samples and 4 features has shape 104. A batch of 32 images has a 3D shape, like 32, 28, 28. Element-wise operations are the power of broadcasting. NumPy applies operations to every element in the array without loops. Adding 10 to an array adds 10 to every element instantly. Array mathematics operates element by element when arrays share the same shape. We can perform element-wise addition, multiplication, or use np ... for the dot product, a key operation in linear algebra. Broadcasting allows operations between arrays of different but compatible shapes. Compatibility means dimensions are equal, or one of them is 1. NumPy automatically stretches the smaller array to match the larger one. Broadcasting is essential for neural networks. For example, adding a bias term to a layer's output requires broadcasting a 1D bias array across a 2D output matrix. This keeps training fast and code clean. Indexing and slicing allow you to access specific elements. You can get a single element using row and column indices, an entire row, or an entire column. Advanced slicing extracts rectangular regions using the start/stop syntax. Slices are views, not copies. Modifying a slice, as shown here, modifies the original array, so use caution. Boolean indexing uses a true or false mask to filter data. A comparison condition creates a mask, and indexing the array with this mask returns only the elements where the mask is true. Boolean masking is perfect for real-world filtering, such as selecting customers over a certain age. Remember to use the element-wise operators, and for and for or, and wrap your conditions in parentheses. Python list slicing creates new lists and requires explicit loops for filtering. NumPy array slicing provides fast, memory-efficient views and uses vectorized Boolean operations, scaling better for large datasets. NumPy provides essential statistical operations. We can quickly calculate the mean, standard deviation, median, minimum, and maximum of a dataset, which is foundational for data analysis and machine learning evaluation. Linear algebra operations are the backbone of ML. NumPy's LINA-LG module handles matrix transpose and inversion. Eigenvalues and eigenvectors, also found here, are used in techniques like principal component analysis. Reshaping arrays is vital for preparing data. You can transform a 1D array into a 3x4 matrix using reshape, or return it to a 1D array using flatten. Use -1 to let NumPy infer a dimension. Reshape logic checks that the total number of elements remains the same. You specify the new shape as a tuple, and NumPy reorganizes the elements while preserving the original data order. A real-world ML example is data normalization. We calculate the mean and standard deviation across features and then normalize the data to have a mean of 0 and a standard deviation of 1. Normalization is crucial because, without it, features with large values dominate the training process. Normalized features allow gradient descent to converge faster and more reliably, improving overall model performance. Computing distances between points is the core of algorithms like k-nearest neighbors. We can calculate Euclidean distance using element-wise subtraction, squaring, summing, and taking the square root, or simply use np.lena_lg.norm. NumPy allows vectorized distance computation between one point and an entire dataset simultaneously. Using axis equals 1 ensures the distance is calculated row-wise, which is significantly faster than looping. The complete KNN process involves loading the dataset, using vectorized computation for all distances, finding the k-nearest neighbors using np.argsort, and finally making a prediction based on the majority label. To summarize, we covered array creation methods, essential array operations like broadcasting and dot product, indexing and slicing, and key statistical and reshaping functions. Here are some practice exercises to build your NumPy skills, including array creation, statistical calculation, reshaping, and vectorized distance computation for finding the closest point in a dataset. Avoid common NumPy mistakes such as shape mismatches, confusion between views and copies. Use dot copy when independence is needed, and using incorrect Boolean logic operators. Your NumPy foundation is complete. You now understand the fundamental building blocks of machine learning. This mastery is the foundation for every advanced ML operation you will encounter. What is next? Pandas. While NumPy provides computational power, Pandas, using data frames, is your powerhouse for cleaning and manipulating real-world tabular data. It handles missing values and joins multiple datasets. Ready to transform messy data into clean, ML-ready datasets? Catch the next video on Pandas, your data manipulation powerhouse.